Hello everyone, I am Poonam Sharma, your science teacher. Welcome you all a new session of Atoms and Molecules chapter. This is chapter number 3 of class 9 chemistry. And this is extremely important topic because on the basis of this atoms and molecule chapter, you'll be able to solve problems in your forthcoming classes as well. Because this is the basic chemistry. So today I'll start with this chapter, atoms and molecules. Before I'll start with this chapter, I'll make you aware about these terms, atoms and molecules. What are atoms? The atoms are the smallest unit which are present in an element. So when an element is formed, it is composed of very small particles or the unit, and we call them atoms. For example, we have different elements exist in nature like sodium, potassium, aluminium, hydrogen. So these are elements which exist in nature. And if we are talking about any one particular element, let's take an example of potassium. So if we take an example of potassium, this potassium element is made up of small substances which we call them atoms. And each of this atom has similar property with that of potassium element. So it means if so many atoms are present in this element, all the atoms exhibit same property. It means this atom or this atom or this atom, they all have same property, which resembles to the property of this potassium. Similarly, in case of aluminium, sodium, hydrogen, so whatever elements we have in nature, all these elements are made up of these atoms, and all the atoms which are present in these elements, they have similar property with that of the element. And if we're talking about molecules, molecules are the smallest unit of compound, we can say that. Like for example, water, it is a compound because it's a combination of hydrogen and oxygen. In previous chapter, we have studied about elements and compounds. So how elements are different from compounds. In compounds, when two or more elements are present in a fixed ratio, we call them compound. So here I have taken one example of compound, which is water. And in this water, if we look at the structure of this water, it contains 2 hydrogen and 1 oxygen. So it means when 2 or more atoms combine together, when 2 or more these elements combine together, they form a compound. And due to the combination of these atoms, when they are chemically combined together, we call them molecules. And these elements which are present and to form a molecule, when these molecules combine together, they form a particular compound. They exist in fixed ratio. Whatever is the nature of that material, this ratio remains fixed. For example, if we take water in the form of ice, in the form of, which is in the solid form, ice form, liquid, in the form of water, or gas in the form of vapors. So water exists in these three states. As we all know that in these three states, water exists in nature. And whatever form is there, in all these three forms, the formula of water is H2O only. So it means the atoms which are present in water, they are present in a fixed ratio. And if we take water from anywhere, any source, from lakes, from rivers, from ponds, from sewage water, from anywhere, the formula of water is always remains H2O only. So we can say that when atoms combine chemically together to form a compound, it is known as molecule, and their ratio is always fixed. So this is how atoms are different from molecules. Now, on the basis of these atoms and the molecules, they are combining and they are forming some substance. This is one example. Like Na combines with Cl, it forms sodium chloride. So there are n number of examples in chemistry in which these elements combine together to form compounds. And these things came into existence after the work done by Lavoisier and Joseph L. Proust. These two renowned scientists, they have given a law which is law of chemical combination. It means when chemically substances combine together, they result in the formation of a new substance. So that law was given by these two scientists. First is law of conservation of mass. Law of conservation of mass states that mass can neither be created nor be destroyed in a chemical reaction. It means whatever reactants we are taking will get the same amount of the products. So whatever mass present in the reactant, and we have already discussed what are reactants. Like reactants are those substances which are involved in a chemical reaction, and products are those substances which result after the reaction of initial substances. So when any chemical reaction takes place, whatever mass of the reactants we have taken, it results in the formation of same number of mass of product. For example, if we are making water, so if H2 plus O, if we are taking H2 and O, so here if we are taking 5 and 5, so it results in the formation of 5H2 only. So whatever mass of the reactant we are taking, it always results in the formation of same mass of product. Or we can say that mass of reactants is equal to mass of products according to law of conservation of mass. Or with the help of this example, it is very much clear how this law of conservation of mass implements. Like we have 10 gram of calcium carbonate. If we are taking 10 gram of calcium carbonate and we decomposes it. So when we are decomposes, here we have taken calcium carbonate which is 10 gram. When it decomposes, it results in the formation of calcium oxide and carbon dioxide gas. So when we weigh these products, first weigh the reactant which is calcium carbonate, and this is 10 gram. So when it decomposes, whatever products we get after its decomposition, we get calcium oxide and carbon dioxide. Then measure these products and we'll get 6.2 gram of calcium oxide and 3.8 gram of carbon dioxide. And when we combine them together, it results in 10 gram. So you can see here the mass of reactant is equal to mass of product. Okay. With the help of this example, it is clear that law of conservation of mass is absolutely correct. So whatever mass we have taken in reactant, it results in the formation of same mass of product as well. Another example I'll take, like here we have taken, this is a piece of wood and its weight is 30 kg and fire is 1 kg. So when we take log of wood and fire, then we burn this log of wood. Now after burning, we'll get these products, ashes and smoke is released. So when we weigh these products, the weight of ash is 28 gram and the weight of smoke is 3 kg. So if we can see that it is 2 kg. 3, sorry. So now we can say that it is 31 kg and here also it is 31 kg. So mass of reactant is equal to mass of product. Now another example which proves the law of conservation of mass is, let's take some ice cubes in a glass which is 100 gram. And when we melt this ice, which is a physical change, because we know that when melting of ice takes place, so there is no formation of new substance, only there is a change in the state. But if ice gets melt and we'll get this product which is in the liquid form, and then weigh this liquid. The weight of this liquid is also 100 grams. So it means it is hence proof that the mass of reactant is always equal to mass of product according to law of conservation of mass. Another example of such kind of law of conservation of mass is sodium carbonate. Let's take sodium carbonate and ethanoic acid. Here we have taken 5.3 gram of sodium carbonate and 6 gram of ethanoic acid. And when we react together, then it results in the formation of sodium ethanoid, which is 8.2 gram, carbon dioxide, which is 2.2 gram, and water, which is 0.9 gram. So when we combine the weight of all the products, it is equal to reactant, which is 11.3 and 11.3. Now this also shows that the mass of reactant is equal to mass of product. So this is according to law of conservation of mass. So I hope from these examples, the law of conservation of mass is clear to everyone. The second law is law of constant proportion, which is given by this scientist J. Prowse. And according to this law, in a chemical substance, the elements are always present in definite proportion by mass. What does it mean? See, when any chemical substance or when any chemical reaction takes place, the elements are always present in a definite proportion. For example, water. If we take an example of water, which is a combination of hydrogen and oxygen. If we take an example of hydrogen and oxygen, as you can see here, the mass of hydrogen is 1 and mass of this oxygen is 8 here. Now look here, this example. Yes. Now they are present in 1:8 ratio. So whether this water exists in solid form, liquid form or gaseous form, the mass is always 1:8. It always remains like this. We need to learn few masses of these elements. So we'll learn these masses later. The mass of this hydrogen is 1 and oxygen is 8. Another example of such kind is, see, when calcium carbonate is heated, it results in the formation of calcium oxide and carbon dioxide gases evolve. And when carbon comes in contact with oxygen, it evolves carbon dioxide gas. Then when calcium carbonate and 2HCl, which is hydrochloric acid, when they react with each other, it results in the formation of calcium chloride, carbon dioxide and water. And another example of such kind is when sodium hydrogen carbonate is heated, it results in the formation of sodium carbonate. In all these examples, you can see that carbon dioxide is made up of same elements, which is carbon and oxygen. Although these are different reactions, but when these reactions are taking place and we get carbon dioxide gas, and the composition of carbon dioxide gas remains same in all the reactions, which is a combination of carbon and oxygen. Here it is present in fixed ratio by 12:32, or if we solve it, 12/32 we'll get 3/8. So it is present in this fixed ratio in all the reactions. So whenever in any reaction carbon dioxide gas is evolved, we always get this kind of fixed proportion by weight. Now I hope till here it is clear to you what is law of constant proportion and what is law of conservation of mass. Now there are some limitations of law of constant proportion. As we are saying that elements are present in a fixed ratio. But if we are talking about isotopic elements, so this law fails in case of isotopic elements. For example, carbon. Let's take an example of carbon. Carbon exists in nature in different form. Carbon 14 and carbon 12. So these are the isotopes of carbon. Isotope means when any element exists in two or more form in nature, we call it isotope. So the isotopes of carbon is carbon 14 and carbon 12. So if we are talking about the mass of carbon in these two, it is quite different. So this law of constant proportion fails in case of isotopic elements. Apart from this, this is not applicable when there are possibilities of making two or more compounds from the same element. If we are using same element for making two or more compounds, for example, alcohol and dimethyl ether. Now, the formula for this is C2H6O. And the elements which are involved in it, carbon, hydrogen and oxygen. And their mass is different in both the cases. So law of constant proportion is not applicable for in case of isotopes or in case of those when the same element we are using for making two or more compounds. So it fails there. Now another is Gay-Lussac's law of combining volume, which said that when measured at same temperature and pressure, the ratio of volumes of reacting gases are small whole numbers. Here you can see, here 2 volume of hydrogen gas combines with 1 molecule of water, which results in 2 volume of water. It results in the formation of, in the gaseous form, in the vapors form. So according to Gay-Lussac's law of combining volume, when at the same temperature and pressure, the ratio of volumes of reacting gases are small whole numbers. So their ratio is always whole number. Now whatever laws were there given by Lavoisier and Proust, they lack this information when it is applicable for the isotopes or if we are using same element for making different compounds. So it is not applicable. Now after that, John Dalton came into existence and he gave his theory on the basis of this atom. He studied atom in detail and on the basis of his studies he gave his theory, and which is popularly known as Dalton's atomic theory. In his theory he states that every matter is made up of very small or tiny particles called atoms. As I told you, if we take an example of sodium, sodium is made up of so many atoms of sodium only. All these are atoms of sodium and they all have same property. And atoms are not divisible and cannot be created or destroyed in a chemical reaction. So they are so small we cannot divide them, or we cannot create any atom when any reaction is going on, or we cannot destroy, we cannot delete, we cannot destroy those atoms which are involved in a chemical reaction. Now third postulate of Dalton's atomic theory is all atoms of a given element are same in size, mass and chemical properties. As I told you, atoms which are present in an element, all the atoms which are present in that element, they all are same in size, mass and chemical properties. It means if the chemical property of this atom And if we are taking chemical property of this atom, they are similar. There is no change in the size and the shape and the mass. So they all are same. But if you are talking about hydrogen, atoms of hydrogen here, properties of these hydrogen atoms are different from those of sodium. But properties of all these hydrogen atoms are same. Properties of all these sodium atoms are same. So this is explained by Dalton's atomic theory. And next is atoms of different elements are different in size, mass, and chemical properties. As I told you, like if you take an example of sodium, hydrogen, aluminium, copper, all these are different elements. And when we studied their atoms, they are made up of sodium atoms, they are made up of hydrogen atoms, they are made up of aluminium atoms, they are made up of copper atoms. Properties of all these are same. These are same, these are same, these are same. But if we compare the properties of atoms of this sodium with this hydrogen, they are different. And properties of this hydrogen and chlorine are different. Aluminium and copper are different. So atoms of different elements are different in size, mass, and chemical properties. And atoms combine in the ratio of small whole number to form compound. When atoms combine together, they are combined in a ratio of small whole number to form compounds. For example, H2O. So when atoms combine in the ratio, so they combine together. Hydrogen combined with oxygen, it forms H2O. So it is combined in the form in a small whole number. The relative number and kinds of atoms are constant in a given compound. So if we are talking about relative number and kind of atoms are constant, let's take an example of hydrogen. Its number is fixed. Hydrogen, its number is fixed. So they are constant. If this water exists in solid state, liquid state, or gaseous state, the number is fixed. The ratio is fixed. It will not change if we take any sample of water, whether we take water from distilled water or from pond, river, lake, from anywhere, or it exists in ice form, vapor form, the combination of this water remains as it is. Now, these are the postulates given by the Daltons in his Dalton's atomic theory. But there are some drawbacks in Dalton's atomic theory. Like atom is no longer considered as the smallest indivisible particle. Because if we take a look of the atom, the structure of atom, which we'll study in detail in next chapter, this atom is also made up of some subatomic particles, which are electrons, protons, and neutrons. Atom is sphere in structure, which is a combination of electrons, neutrons, and protons. So earlier, Dalton was saying that atoms are the smallest unit, but it is not actually true. Atoms are also made up of electrons, protons, and neutrons, and we call them subatomic particles. So this is first drawback of Dalton's atomic theory. Second is atoms of same element may have different masses. He was saying atoms of same element have same masses. But if we look an example of atom of chlorine, chlorine has different masses like 35 and 37. Chlorine exists in different forms. So here we are saying if we are talking about the isotopes, so atoms having same element but different mass number, we call them isotopes. So his theory failed in case of isotopes. So when we are talking about masses of atoms of chlorine of different which exist in different forms in nature, which is known as isotopes, their masses are different. So this is failed in case of isotopes. Then we have atoms of different elements may have same masses. Sometimes atoms of potassium. Example of such kind is, if we take an example of potassium and calcium, they both have same masses, but according to Dalton's atomic theory, atoms of different elements have different masses. But here, if we take these two examples, their masses are same, and these are known as isobars. We have studied about isotopes and isobars in chapter number 1. So his theory failed in case of isotopes as well as in case of isobars. Now next is substances made up of atoms. Substances made up of same kind of atoms may have different properties. For example, charcoal, graphite and diamond. They all are allotropes of carbon. And what are allotropes? When any element exists in nature in two or more forms. So we call them allotropes. So carbon exists in nature in charcoal, graphite and diamond form. If we are talking about this, these allotropes of carbon, they have different properties. Charcoal, graphite and diamond, they are entirely different from each other. Graphite is black in color, diamond is shiny in appearance. The properties are entirely different. They have different physical properties. Graphite is a good conductor, it is quite soft, but diamond is the hardest substance known. So these are the different properties. So in this way also his theory failed. Now next drawback of Dalton's atomic theory is the ratio in which the different atoms combine to form compound may be fixed and integral but may not be simple. For example, sugar, its formula is C12H22O11. As you can see here, it contains carbon, hydrogen and oxygen in the ratio of 12, 22 and 11. But fixed. But it is not simple. And it is very complex. So here also it is failed. So these are the drawbacks of Dalton's atomic theory. So after this, we came to a conclusion that Dalton's atomic theory was also not 100% correct. And now few scientists work on the name of these elements. We are using Na, H, C, O. These are the symbols which we are using for depicting particular element. And for depicting these elements, we use these symbols. These symbols basically come from their name. Like if we talk about hydrogen, we always choose first letter of the element. Hydrogen starts with H and we represent this by capital H. First letter is always capital. But in some cases, we use their Latin name or Greek name. For example, if we are talking about sodium, sodium. And if we are talking about sodium, its name is natrium. This is the Latin name of sodium, natrium. So on the basis of this Latin name, we have given this symbol Na to it. Apart from this, there are certain more examples. Let's take those examples, their Latin name and their elements and their symbols. Although in all the elements, we always take first letter of the element and first letter is always capital. For example, in case of aluminium, first letter is always capital and second is always small. And sometime if we give name to any particular element, it is not necessary that we always take first two letters. We can skip letter, any letter, or we can choose any other letter. Like in case of chlorine, we have taken first letter and third one, but second letter is always small. And here certain elements like Au, which is silver, but its name is or it's gold, sorry, it is gold, and its symbol is Au on the basis of this Latin name. Apart from this, silver, if you're talking about, it is silver. Its symbol is Ag and its Latin name is argentum. So these are Latin name of these elements. On the basis of their Latin names, we have given them these symbols. Apart from this, like magnesium, it is represented by Mg. And as you can see, second letter is always small. Now, another examples of such kind of this is cuprum. Cuprum. This is copper. So instead of giving symbol Co or C2E, we have given Cu and its symbol is this. So these are different elements. Many more examples are there. On the basis of their Latin name, we have given them these symbols. But earlier, before the existence of these symbols, the elements were represented by some marks. Like hydrogen is represented by this circle and one dot into it. These are the symbols given by Daltons. And then second is carbon. Carbon was represented by this. It is completely covered, shaded, yes. So these are the symbols given by Dalton, but later these symbols came into existence. Now these are known as the modern symbols of elements. And these symbols were given by Berzelius. Berzelius, because it is easy for us to represent elements in a chemical reaction. And silver was represented by this. So these symbols were given by Dalton, and these were given by, all these were given by Berzelius. And these are known as modern symbols. These are known as modern symbols. Now let's study about atoms. As I told you, atoms are the smallest particle of an element which can take part in a chemical reaction. And size of atom is always measured in nanometers. It is so small, it is always measured in nanometers. This is the unit in which we measure the size of an atom, the radius of an atom. Like this is an atom and this is the radius. So this is measured in nanometer. And 1 nanometer is equal to 1 upon 10 meter, or atomic radii of hydrogen is 1 into 10 raised to power minus 10 meter. Now this is how we represent atom. So atoms are the smallest particle which are present in an element, and it is size of atom is represented by nanometers. So these symbols I have already discussed with you. These are the symbols which were given by Dalton: hydrogen, carbon, oxygen, iron, sulfur, copper, lead, silver, platinum, mercury, gold. But nowadays we are not using these symbols because it is very complicated to draw these symbols every time for writing a chemical reaction. Now these symbols, which are known as modern symbol, which were given by Berzelius, nowadays we are using it, and they are their Latin name. Hydrogen represented by H, helium represented by He, carbon represented by C, copper represented by Cu, cobalt Co, chlorine Cl, cadmium Cd, boron B, barium Ba, bromine Br. And why we have chosen different symbols for them. Why we have chosen this Latin name? Because as you can see here, these elements starts with same alphabet. So it is very difficult to recognize these elements. That's why few symbols were taken on the basis of their Latin name, or some symbols were taken on the basis of their first or third alphabet. As you can see in this case, carbon represented by C, copper given by on the basis of this Latin name, which is cuprum, cobalt CO, chlorine C and L, cadmium C and D. So it is easy for us to distinguish between these elements. Otherwise, it is very confusing if we'll write same element. Now, here sodium, which I have discussed, Latin name is natrium. That's why symbol is Na. Because sulfur also starts with H, silver also starts with S. Potassium, calcium, and its symbol is K. Iron, its Latin name is ferrum and its symbol is Fe. Gold, aurum, Au. Silver, argentinum, symbol is Ag. Mercury, it is represented by Hg. So these are the symbols of these elements, and you have to learn elements at least till atomic number 20. So just learn atomic number these elements till 20. Now come to molecules. Molecules, as I told you, the smallest particle of an element or a compound. Why we are saying smallest particle of an element? See, if element exists with other element, some elements are there which do not exist in nature in free state. So they exist with some other element like hydrogen. It always combined with hydrogen. So here two molecules of hydrogen are present. So it is the smallest particle of an element and they exist independently. Molecules of an element constitute the same type of atoms. So if we are talking about this hydrogen, which is a combination of H and H, properties of both the hydrogens are similar. Our molecules may be monatomic, diatomic or polyatomic. Here it is diatomic. When it is 3 like nitrogen, so it is triatomic. Oxygen, it is diatomic. And if we talk about helium, which is an inert gas, it is monoatomic. And if we talk about sulfur, it exists with 8, so it is polyatomic. So these are the examples of different kind of molecules which are monoatomic, diatomic and polyatomic. Monoatomic is helium, which is an inert gas. Diatomic, hydrogen, oxygen, and polyatomic is sulfur. Many more examples are there. Then if molecules of compounds join together in a definite proportion and constitute a different type of atoms. It means when molecules of compounds join together, when these molecules combine to form compound, they exist in a definite proportion and constitute a different type of atom. It results in the different type of atom. So now number of atoms present in a molecule is known as its atomicity. For example, helium, it contains only one molecule. It is monoatomic. The number of atoms present in a molecule is known as its atomicity. Neon, these are inert gases. Helium, neon, argon, so they exist in nature in a monoatomic form. Sodium, it is also monoatomic. Iron, monoatomic. Aluminium, monoatomic. Hydrogen, H2, as you can see, where 2 is written, they all are diatomic. Nitrogen is also diatomic. Phosphorus, 4, tetraatomic, yani polyatomic, more than 3, या more than 2. Sulfur, octa, polyatomic. So these are the examples of different elements with their atomicity. So I hope till here it is clear to everyone. Go through this topic thoroughly. And if you'll face any problem, any doubt is there, you can ask in next class. Till then, take care and bye.